So we are back on GPUs, and I figured I would rewind a couple of slides so the latecomers can also catch up, have a chance. So this was one of the key slides I wanted to show you, where I pointed out that GPU computing is not just GPU computing. Right? So GPU programming is not just GPU programming. You actually write code for a hybrid architecture, and you write CPU code and GPU code. Okay. So this was the skeleton, how the program runs. You have the CPU code, the host is running the usual app that you have that fires up, essentially launches these GPU threads. It's called a kernel launch. And while that's running, the CPU can keep on doing work. Okay? And then when you are done with the GPU computation, you really need the results, then you can synchronize and use the results. So this was the Hello World application, and we'll be writing code real soon that is much more complicated than this. Well, not that much more, but actually compiles and runs. And this is where you invoke in the C code the kernel itself, specify how many threads you want to run, and then within the threads, you figure out which data you want to work on, and then just do the task that you are programmed to do. Okay, that's this bit. All right. So now the syntax. Okay, you noticed already the global keyword that is in the previous example. That's what determines what the kernel is. Okay, that's the GPU code that runs on all the cores. Now, there are other keywords that are very important, and that's what you will actually use in your C code to tag different functions. If you call something a host function, that's a piece of code that's only compiled for the CPU. If you call something a device function, so if you have a C function and you have device in front of it, that will be compiled for the GPU only. Now, you can mix these. You can have a piece of code, the same C code, the same C function that's compiled for the CPU as well as the GPU. Okay, these are two separate binaries that gets run on separate devices. Okay, and then there is the kernel launch, for which there is a special construct in this new language, in this C4 CUDA language, if you like, that simplifies essentially all the magic that happens in the background launching the kernel. So in this triple brackets, you will specify all the parameters that's required to launch that kernel. Essentially, how big the blocks are, how many blocks you have, and so on and so on. And there are other things as well, optionally. We probably won't get there. Okay, so that's the syntax. Okay, the kernel is, as you saw it, very much like a normal C function. There are a couple of exceptions. So the kernel function can never return a value. Now, how could it? If you have 75,000 copies of this running in parallel, how do you deal with the return value? So what they do is, as we looked at the pointers, right, they will essentially output they put the results into a piece of memory, so that you have to allocate again room for those, and they just run and save the results. Okay, inline functions. Okay, so that means that essentially kernel code that you write can use functions that you declare as device. Those functions will be inlined. What does that mean? So inline actually doesn't. So it actually, sorry. Exactly. So the code is actually pasted in, right. So you don't jump out. So sometimes what you have in CPU code, that the procedure that you have to run, or the function that you have to run, is sitting somewhere else in memory, and you sort of you jump out over there, you run that piece of code, and you jump back. Now, in CUDA world, for efficiency, and this is what CPU compilers often do as well, the inline functions, that you don't do this jumping out and back. But it also means that if you have lots of function calls, they just get duplicated. So they have actually inline. So there's some more, which is okay. There's nothing special about it. Now error handling gets tricky, of course, with this many threads around, and exceptions that are very nice usually to use for error handling are not available. So you have to do you have to essentially use return values or some other ways of communicating if you encounter some problems. Okay, so the built-in variables are critical. This is what you use in your kernel to figure out who you are. Okay. So, like we said, the threads are the basic operations that are listed for each piece of data that you can run. So now those are identified by this variable called thread ID X. So this is always available in your kernel. You don't have to declare it. The block is also available as a block ID. So this is telling you, which block this thread lives in this whole grid of blocks. Okay, and then you have the dimensions of the block itself and the grid itself. So how many threads are in this block? That's defined by this thing, and how many blocks are in the grid. Now, notice these are different types. These are special types. That's because, again, these are not just linear things. A block of threads can be rectangular or can have 3 dimensions as well, just to make it easier for you to map the processing onto your data. So if you have 3D data, often it's very convenient to use a 3D block of threads to process that. Okay. All right. So the new types that are very convenient and they are very efficient, actually the GPU code knows about them. So these are first-class citizens, essentially, in GPU world, are simple vector type things. So an int2 would have 2 integers in it, and you refer to them as .x and .y. And a float 3 or a float 4 will have x, y, z, w. Okay, these are just very simple structures that you can make use of very efficiently. Again, you can see how this is coming from sort of computer graphics, where you have x, y, z in 3 dimensions and maybe some color or alpha blending or what have you. Okay, the dimension is very similar to a 3D integer, like a uint 3. The difference is that when you don't initialize certain components of it, then they automatically revert, set to 1. So that means that if you have a 2D block of threads, then you have the x and y direction, and the z is always just 1. Okay, so very simple. Underneath, they can work with this. All right. Of course, now you have a bunch of new features in the language, so you need a compiler that can deal with it. And that's called the NVCC, the Nvidia Compiler, to essentially pre-process these special constructs. And that really is just a wrapper. Okay, just like you saw it before with other wrappers and compilers. Same thing happens here. There's a pre-processing step that essentially figures out what part goes for the GPU. The GPU code is compiled underneath separately, and so on and so on. Okay, but when you compile code, when you will soon compile code, then you will be using this compiler. Okay, so this will do both the CPU and the GPU underneath. You can parameterize it to just do certain parts with it, as usual, with any compiler. But this is best done in just practice, I guess. We'll look at this. Okay, so at this point, you could even start writing code. I mean, we could even look at the very first example right away. But I thought that we should just get all the slides out of the way. And before we launch into coding, we look at the famous bottleneck of GPUs. Right? So people say that memory access is expensive. And that's definitely true. I have to say that that said, still much better than CPU. Okay, so GPUs have fancier memory, they have faster memory, and as long as you obey certain basic rules, then you will get really high bandwidth to memory. Okay, so there's nothing to be worried about. But that said, I wanted to just draw your attention to these things and have some of these things out of the way. So, as we said, processing in parallel, that's easy, right? You just fire up your threads just like the vectorization, the vector addition was in the previous example. But then when you have to communicate with each other, or you have to do something more than that, like aggregation, reduction type of operations in the map reduce, right? Then you have to think a little bit. And so typical operations include count, sum, min, max, the usual stuff that you will do. If you want to say normalize a vector, you have to figure out the norm of a vector. Right? Figuring out the squares of the components is very fast. You can do it in parallel, but then you have to add things together. Okay, so things that were simple before might not be as simple now. And again, sequential work just has different complications. So in this case, you can, for example, just compute the dot product of two vectors like this. Right? We had the code on the slide before, essentially the same code, not addition but multiplication, and then just have to add it up. So that's the reduce step. Okay. So how can you reduce? How can you add up things? Okay. Well, you have to be a little bit smart about it. So the different strategies that people have developed are essentially building on pyramid-style additions. You start with, okay, you can imagine how it works, right? You take two, and you can have many threads that take two components, they add them up, and then that partial result will have to be added up again, and just have this pyramid that builds up. Okay. All right. All right, so this is something that is really important. The memory is accessed. And the truth is that it's important to understand how memory is accessed, not just for GPUs, but also for CPUs. Right? So if you have a matrix, just we had it on the previous example, where the data is essentially in rows, but the rows are linearly put down next to each other, and you have essentially pointers pointing where the rows start. If you access elements in an order, I thought I put it in, sorry. If you access elements that are next to each other in memory, that will be much, much faster than incrementing the other index that jumps in memory. And the reason is that every time you read something, every time you read something, the hardware underneath the instruction will read more bytes than you need and will cache it. So if you have that, you have your code reading in the right order, you will be using the cache. And if you don't have it in the right order, it's called a cache miss. So this is significantly slower. All right. So in Nvidia and GPU world, it's called coalesced memory access. So all the threads can get the values, single instruction, right, in your CUDA code. Get the AI component, the ith component of the A vector. They can get that. It's a single instruction in C, but they also on the hardware they can do it at the same time as long as the components are next to each other. Okay, if they are all scattered in the memory, if you don't have I sitting in there, but you have complicated expression that involves I, that's doable, but the memory access might take much longer. Okay, so that's the kind of thing to watch out for. It's called coalesced memory access. Yes.
A couple of simple questions.
Yes.
First of all, do you have to run on all the cores in the GPU, or can you choose how many threads? How many, not threads, can you choose how many cores you're running on?
Yes, you can choose how many threads, in fact. So the example we had on the slide was running n threads in a single block. So, and there are limitations on how many threads you can have in a block. and also how many blocks you can have in a grid. But essentially, yes. So you can by when you launch the kernel, you can specify how much you need, and then if you don't need all of them in the kernel, you can just let them idle. But yes.
The second question was, somewhere in this hierarchy of threads, blocks, grids, you have shared memory within some of these, not across others. Is that you're shared in a block? Is that how it works?
Exactly, yes. So the multiprocessor can run some number of blocks, and that is typically that changes. But what's guaranteed for you that within a block the threads can share memory, and this is not much. This is 64K of shared memory, but that's very fast. So
that's where you can put your partial sums.
For example,
right?
That's right.
And then at some point you have to sum across blocks.
Exactly.
In the grid.
Exactly.
And that is done how?
So when a block finishes, you have to save your partial results in global memory. Okay. So that has to be done. But by then you have completed 1,500 threads or so. So yeah. Yeah. So when you get to programming shared memory, we won't get there probably today. But that's when it gets really exciting, when the threads really start collaborating with each other. But it's worth writing a simple code first. So without thinking too much about shared memory. The reason is the new architectures have something called an L1 cache. So without explicitly programming the shared memory, it's the same chip. It's just partitioned into shared memory and L1 cache. You can actually make advantage of this chip even if you don't program it, and then you let the compiler choose the best options, but that could be good enough. Yes, there was another question there. Right. So this is actually interesting. So the number of threads you can run is constrained by a bunch of things. Okay. There is the maximum that device is capable of running, the multiprocessor is capable of running. But there is also limitations on how much shared memory you need. So your thread needs a given number of bytes per thread in shared memory. That might be a constraint that will reduce the number of threads you're allowed to run. If you need lots of registers, for example, in your code, that might also be something. So the multiprocessor has fixed number of registers. If you need something that has 30 registers used, then potentially your number of threads will have to go down. Okay, so it's called the occupancy. There is a CUDA occupancy calculator available online. You put in what card you are using, what the CUDA version is, and so on, and what the block size is, and what the shared memory requirements are, and all those things, and tells you what your occupancy is. Are you running 30% of the threads that are available, or are you running 50% of the threads that are available? If you are in that ballpark, a factor of 2 from optimal, then it's not so bad. Again, remember there are other things that come into play. Memory access, important, right? So shipping data. So it's not always worth trying to go for 100% occupancy, because maybe it comes at a cost. So maybe by reducing the register numbers, so the number of registers that you are using, you have to essentially save variables during execution into global memory, and that is an expensive operation. So maybe it's possible to have 100% occupancy, the cost of global memory access in your kernel, and that might just slow it down much more. So there's an interesting optimization question hidden in that question, and that's something that we won't get to today. But I think that's okay. So just in principle, it's best to just write your simple first design, okay, And then you can start tuning it, and you can start optimizing it, and try different things. Changing the kernel size, or the grid size, the block size. These kind of things can actually have a significant effect on your performance. That said, oftentimes it will not make too much of a difference. So don't worry about it just yet when you start programming for GPU. Okay, any more questions? Okay, just be brave. Okay, don't just let it go. It will work. So this is just a quick example for you to see how this reduction could go, essentially this pyramid style. And of course, there are again different kinds of patterns you can imagine here. So this is one of them, and this is another one, right? So as you can see here, you're looking farther away. Here things are more aligned. These potentially have performance impacts. I won't go into this very much, but just keep in mind that if something is not running very fast, maybe you should look at memory access. Okay. All right. So this is the hierarchy that I wanted to talk about, and this is kind of important, even though we probably won't be optimizing our code just yet too much. Okay. So there's global memory. That's the big piece of memory that's on the card. Okay. That's 3 gigs or something. And then there is a small memory, the shared. It's 100 times faster, and it's right there on the multiprocessor. It doesn't go all the way to the global memory to fetch the values. And that's something where the threads within the block can communicate. Okay. And then there are the registers. So that's per thread. Every thread will have 12 registers, or you name it. Okay. And that's something you eventually start watching, because the more registers you use, the less threads you can run, and so on and so on. Okay, so then there is an L1 cache, which is essentially what I mentioned. It's just a shared. It's on the same chip. It's the shared memory versus the L1 cache. You can configure it whether you want, 16K of shared memory or 16K of L1 cache, and then 40K will be the other one. In addition to that, you also have constant memory. Okay, and constant memory is something that you can just essentially from the CPU. It's like an API call. You ship some data to the GPU, and then that will be available for all the threads. It will be fast, but you can change it. Okay, and there are textures and other specialized things that I won't get into. Okay, so how does this look in terms of hierarchy and the schematics? Okay, so here's your host talking to the GPU. Okay, and then you have the global memory. So that's the big chunk there, and constant memory is the small piece, and then you have essentially the blocks of the grid, and within the blocks you have access to shared memory and the registers for each thread, and then you have the local memory. Okay, so that's how it all works. So you want to essentially stay in registers and in shared memory when your threads are running. Otherwise, again, the global memory is a shared resource, right? So then you have to worry about who writes to which part of the memory and these kind of things. So typically, this is handled by smart indexing. Yeah. Right? So every thread knows where their data comes from. Every thread knows where it's supposed to write, and you just don't write on top of each other. Okay. If you do, what would it happen? What would happen if you wrote to the same location? Right? They run in parallel, potentially. I mean, within a block, you don't know. Within a block, they run in parallel. Out in the kernel, you don't know. Right. So what will happen is that it's not determined. It's non-deterministic. So somebody will get to write, but you don't know who it will be. So that's dangerous. Okay. So then, so the threads have the registers, blocks have the shared memory essentially to themselves, and then the grid have the global memory. Okay. So shared memory is something that you program by using a special keyword called shared. And again, when you declare the array or the variable, you can just stick this on top of it. and you can also, okay, I don't discuss this too much. You'll get to this essentially on your own, I think. So synchronization is important, though. Right? So as soon as you start, yes. Fantastic. That's good news. Congratulations. It is. Very good news. Thank you. All right. So how do the threads communicate in a block? Okay. So this is kind of interesting. So they can't fire up, calls into each other or anything like that, or call each other's functions. It doesn't work like that. What you can do though is that you save partial results into shared memory. Okay. So everybody can save the results in shared memory. And then somebody else can use that result. Before that happens, you have to make sure that all the threads are synchronized. Right? You cannot access one thread's output from another thread before synchronization happens, because even though they could be running in sync. So 32 of the threads will be running in sync, which is the warp. But typically, they will not be in sync, right? So, or they might not be in sync. So you have to issue essentially a synchronization, and that's for a reason, right? So if they access memory, for example, they will be accessing essentially memory potentially sequentially. Who knows how the memory requests are actually done in your code. So the synchronization is something that costs you. Again, the philosophers will have to wait until everybody eats, right? So that's a synchronization thing. But after the sync threads function in the kernel was called, you know that everybody's results are saved in shared memory, and I can go and fetch it. Okay, that's basic communication. All right, so yeah, and there are fancy variants of this that actually can count. For example, if every thread has a Boolean variable that says whether it found an interesting event or not, then you can do a sync thread, and at the same time, the hardware can count how many of them found something. Okay, and based on that, you can decide whether you want to run further, or you want to do copies, or you want to rearrange the data, whatnot. So, okay. Okay, and I left this for the last because I saved this for the last because this is sort of an easy way out. Okay, so these operations called the atomic operations, which guarantee that all threads get to do what they wanted to do. For example, atomic add. If you want to add up a bunch of numbers in an array, okay, then you can either do the reductions that we talked about before in a pyramid style, and that will run really fast. Or you can just be lazy and say, oh, I want an atomic add on all the threads. Now that will be expensive, right? They will have to do some sort of blocking. They have to make sure everybody gets to write. And that's something that's not encouraged or recommended. But there are ways, or there are sometimes cases when it can be avoided. So when you do these kind of things, you probably want to do it in shared memory, so it's less threads to worry about and also faster access. Or if it's happening on the grand scale, then you can make sure that only one thread does this in a block. Right? These kind of things you can play the tricks with. Okay. All right. So I mean, actually, all right. So here we go. So let's actually look at some examples. That's the best way to do this anyway. Okay, I just have some of these things loaded on the web. All right. Okay. All right. Let's do this. So here's a very simple kernel, the same thing that we actually had running or on the screen as a hello world. It's called an add kernel. Okay. This kernel right here. So it takes essentially takes two arrays, A and B, and it outputs one. Okay, so what this does is it figures out again which thread I am, the same example we had there, and does the memory access, gets AI and BI, and then writes CI. Okay, so that's the kernel, the global. Everything else is normal C. Okay, this is not the best way to do things. I mean, you typically want to get your kernels big and beefy, so it does a lot of things for you. But this is just the simplest thing you can do, right? All right, so let's look at the main function, right? That's where the execution starts. Again, it's very simple. We don't worry about efficiency. We don't worry about anything right now. I just want to show you and explain what happens. Okay, so step by step. And this is actually code that you will compile this code and you will run this code. Okay, soon. As soon as yes. Oh, I'm sorry. Did it beep? Okay. It's coming on? Okay, so it's very simple code. The array size is 5. Okay, so we'll be running 5 threads. Okay, this is not the way to use GPUs, but just for illustration purposes, we'll be using 5 threads. Okay, so the array A is just 1, 2, 3, 4, 5. Array B is 10, 20, 30, 40, 50. And we'll be adding these 10 numbers. Okay, that's all we're going to do. But we'll do it with proper queuing and do it all the way. So let's see what happens. All right. So in line with the CUDA conventions, and very much like what BLAS or LAPACC does, we are not returning values even from this function on the CPU as a return value, but we use that for CUDA status, error handling. Okay. Again, we mentioned that there is no exceptions in here now. So this function will do everything. Okay. So this function add with CUDA will add A and B and return C, and the arrays has also passed in, so it can do something with it. And in the end, we just print out the result. Okay. That's all we're going to do. And then at the end, you have to just reset the device, so you release it. Okay, so let's look at add with CUDA. That's the function that does all the work. Okay, so it gets pointers to A and B and C, where the output go, and it declares device pointers. Okay, so these are pointers, much like the pointers you're used to or what we had before, except these point to memory on the device. Okay, and these are just initialized to 0. Okay, first thing to do is grab the device. Okay. CUDA set device will go and get device 0. You can have multiple GPUs in a system. Okay, you can actually query how many GPUs there are, which GPU is what, and figure out which device you want to use. And you can use multiple devices. Okay. In this case, we just use one device and grab that. And again, check the status. If it's a successful request, then we are done. We can keep on going. Okay. I don't use error messages or what's it, go to commands usually, but this is an example that came from the Nvidia developer toolkit, so I figured I just stick with this. Actually, is in this case quite handy. You'll see in the end. Essentially, yeah. Anyway, so all right. So we have claimed the device. So now next thing we do is we allocate memory on the device. Okay, same thing we did with malloc, except again, we are not returning the pointer that we allocated. But what we do is we do this trick. This is the pointer-to-pointer trick. Okay, so we have the def C, which is the pointer. Now we steal the pointer to that pointer and pass that in, okay? And then CUDA-malloc will allocate memory and load the pointer to that memory onto that location of the memory. Okay, so the CUDA-malloc will do the allocation of this size array of integers. Okay, and again, check your status. If it's all fine, then you can keep on going. Okay. You see how this works, right? This pointer thing. Yes, yes, yes. Okay. If not, let me know. All right, so now you do the same thing for the A vector and the B vector. Just allocate some more memory. Okay, and now comes the copy. Okay. So we had A and B and C. Well, C is none, but or null. But we had A and B loaded and sitting in CPU memory or host memory. Okay, so that's your A pointer pointing to that memory. So what you do is you do a memory copy using CUDA mem copy, and destination, source, and then how many bytes you want to copy, and then direction. Yeah, you're copying from host to device. Can you read that? Okay, so you're copying from host to device. Again, just one line, but there's some error checking afterwards to see if it all worked. Okay. And then copy B as well. So now we're ready to go. The GPU has both arrays sitting on global memory, and now I can fire up the kernel launch. Okay. So now the magic in here is essentially the number of blocks. I just need one block in this case because I know that a block can have 1,535 or 36 threads, and then the size is the number of threads I want to have. If it's just an int, it knows that it's just a one-dimensional thing. If you actually specify two-dimensional, three-dimensional dimensions there, then it will adopt and do it that way. Okay. So and then you specify the device pointers. Okay. Remember, the kernel had a C pointer, an A pointer, and a B pointer. That's all we had up there in the kernel. Now that's what we have here. Okay. And then the limitations on the kernels are all available through the built-in variables. Okay, so thread ID X, block ID X, and so on and so on. Okay, we had a very simple kernel which didn't look at these at all, but we'll have more complicated ones that will actually obey and will run for more bigger arrays as well. Okay, so this is the kernel launch. So when this happens, immediately returns. And so this will return immediately, and then you can do your CPU processing in parallel with the GPU processing. And then when you need the results, you say, CUDA device synchronize. That will actually wait and block. It will wait until the CUDA is done processing all your blocks and then returns. So then you can check your status as usual, and then dev-C, the pointer on the device, now has the results, right? The results are all sitting in there. So now I can copy it back. I do a CUDA mem copy device to host and have my C array populated with all those values. Okay. This is broken down step by step, but this is what it takes to run something. It's very simple in the end, right? So you just you put the data on the GPU, you process, and you take it back. And the processing is happening in parallel. And then you just free up the memory on the device, CUDA free. This is where the error is in there, so you can always free up the memory before you exit. And then you return the status, and that's it. Oops, sorry. This is the whole code. Okay. Any questions about this? Sorry? It is, yeah. I mean, this is the lowest level thing that you can think of. But this is the framework. This is, I mean, you can write it shorter. But the idea is that here you can actually see step by step what happens. Okay? And this is what logically you have to do. You have to transfer data there, do things on it. Unless you generate the data right there, right? Then you don't have to transfer back and forth. I mean, eventually you have to get something out of it, but okay. It's a very simple pattern. Okay, so now, yes.
So much data that you overflow a block.
Yes.
Then you've got to be managing the blocks.
That's right, exactly.
Example.
That's the next thing I want to show you. Yeah, this is exactly the next thing. So here's the next example that does the same thing we talked about, except now we want to do it on 100,000 values or something big. And now you really have to think about blocks and threads. Maybe before I do it, let me just explain what happens when you actually run the kernel, right? So the kernel launch will essentially launch, in this case, a single block. And within that, it's specified that there's only 5 threads that's required. So the minimum of so there will be one warp running on the GPU. So the warp will have 32 threads in it, but out of the 32, 27 will be just idling, and the 5 will be doing the addition and so reading A, reading B, adding, and then writing C. So that will happen on only 5 of the threads, and the other 27 will just idling. Okay, so let's do the same thing, but now do it on something bigger. Okay, and I have these codes for you later to look in. And okay, so and also it seems like I have a function for it as well, just to make things more interesting. Okay, so now we have again an add with CUDA function that's declared up there that now has the output C array, has the size of the whole problem, and we'll pass that in. And then it has the A and the B, which are the input arrays. Okay. We also have a function add-ints that just returns the sum of the A and B, which is compiled for both the GPU and the CPU. So if you have a piece of code that's non-trivial and you want to debug that, you can debug it on the CPU. You can see what happens. You can have it on the GPU. The same piece of code compiles to the GPU code as well. Okay. And now, yes. Well, like I said, it's an inline function. So whatever is in the body of this function in the assembly language or the machine language, it just gets inserted into the code. So no, actually it doesn't. Okay. Sorry? Of lines? Not really. No, I mean, programs require memory, but no, not really. At least not that I know of. If you find that there is, then let me know. Yeah, I haven't run into this. Okay. I don't think there is any practical. Okay, so here's the kernel. Okay, so this is the important part. So now we have, or shall we look at? Okay, let's look at the main function first, and then come back for the kernel later. All right, so the main function starts out with a big array size of 100. That's a million, I guess. Is it a million? A million elements. Okay, so we have A and B and C declared and allocated in C as host memory. And then we fill it up with A and B being some values. Okay, and then we want to add it in parallel. So we just call our add with CUDA function again with C, the array size A and B. Okay, same thing. And now let's go to that function. And the same thing happens. We declare A and B and C on the device, okay? And then we grab our CUDA device, the set device. We allocate memory for C, A, and B, same way we had it before. And then copy A and B so the GPU has all the data available. Okay, so now comes the kernel launch, and this is where we start worrying about threads and blocks. Okay, we have to specify how many threads we want, and this is a free parameter per block. This is a free parameter you can play with, how you want to chunk it up, and it will have some effect on the speed and the efficiency of the calculations. But as long as you stick with reasonable numbers, it will not be a problem. And again, there is the occupancy calculator to help you pick these values if you want to. So we just picked 256 threads per block in this case. Okay, so then we figure out how many blocks we need. Okay, so the size is 1 million. Okay, so we need some number of blocks Each of that is 256, such that it's a little bit more than a million, but not much more. Okay, so there will be, in the end, there will be one block that's a partial block. Okay, and the way it's done here is that you add the number of threads per block minus 1, so, and you divide it by the number of threads per block. So what happens in C or integers is that essentially when this division happens, it gets truncated. And because we added n threads per block minus 1, it's essentially a roundup. Okay? This is a very simple way to just do essentially a roundup of what comes out. So this is the number of blocks we need. And then we call the kernel with the number of blocks, the number of threads per block, and the parameters we had before. Okay, same thing. Almost the same thing. Actually, we have the size that is passed in right now. So everything else down here is the same. We synchronize, we copy back, and so on and so on. So let's look at the kernel. How did the kernel change to deal with essentially the blocks and the threads? Because that's where essentially everything happens. So if you understand that part, then you're ready to go and do the programming. Okay, so let's look at this kernel and make sure that everybody understands what happens in this kernel. Okay, that's not crazy. All right, so this is just one page. Okay, so first of all, now we have multiple blocks. Okay, and we have to figure out which piece of data we should be working on. Okay, so what you do is you figure out first, what block you're in, the block ID, so X because it's just one-dimensional. So the block ID X will tell you which block you're in, and there's a block size that you have to multiply with. Okay, and then there is the thread ID that tells you within the block which thread you are. Okay, so this tells me that based on these built-in variables, this thread running in parallel should be working on the ith element of the vectors. Okay, now there's one more thing we have to do. Because we allocated more threads than we actually need, at least for one block, the very last block, we have to check. We have to check if this, it's a bound check, right? We have to check if this index is not out of bounds. Otherwise, you will be accessing memory outside what you allocated. Okay, so have an if I less than n. As long as you're under it, then that's fine. Everybody is running. But if you're not, then those threads should not run. Right? So those will be just idling while the other ones are running. Okay. If you have if and else, then because it's SIMD, everything is running together. Okay, all branches will run. So if there are some threads that on different sides of the conditions, then you run one of the branches first. I don't know which one, because it's not deterministic. So you run either else or the if branch, and while you run on all the threads, a bunch of them will be idling, and then you get to the other branch, and then the other one will be idling, but you run them through, right? So this is why forking and if statements, conditionals, are not necessarily a good thing to have in SIMD architectures, because then you are essentially running twice the work. Okay, so it's not if or that, but both will run. So okay, so then the calculation happens, and it's spelled out so that you actually see, and I can say which line does what. Okay, so this is the line that I could have written or we had before, but now it's all spelled out step by step. So first, you have to do a memory access. Okay, so essentially fetching the ith element of a vector in parallel. Right? All the threads are going to do a read in parallel and store it in a local variable that's sitting in register. Okay. Even if I wrote this code, the same thing would happen, right? You have to fetch that memory from memory and save it in register. And then you fetch the bi element, okay, again in parallel. These are all call access. Everything is coming in very fast. And save it in register. And then you do whatever you have to do. Okay. can be an inline function, can be anything. So here you want to do lots of calculations, right? That's the whole point of doing GPU programming, that now you can do lots of things essentially for free. Okay. And then once you are done with that, and again, you have something in the register, then you can write it back. Okay. Now this is a global memory write. This is again coalesced memory write. But so these are the expensive operations, right? As simple as they look, and this is essentially free. Here you can do anything you like, almost anything you like. Okay. So I won't talk about debugging code very much, just because it just it takes too far, and we don't actually have the tools to do it in a simple way that would be demonstratable. But I'll point out for those who will actually get into debugging GPU code a bit of detail, which is that the Nvidia compiler for the GPU is extremely aggressive. It optimizes away everything it can by default. And the reason for that is if you don't do it, then you are essentially running a different kind of program. Right? If you decide to use more registers than you require just for debugging purposes, then your execution order will be different, your will be different, and the whole execution essentially of the code will be different. So now what does that mean? It means that, for example, in this case, I'm pretty sure, if you run this through the debugger, as soon as you do the addition, one of the variables will disappear, A or B. You won't see it anymore. Why? Because the C overrides that. Right? So there's no need for 3 variables in this function. You only need really 2. Right? You need A and B up to here, and then when addition happens, then one of them can be thrown away because I only need this TC in the end. Okay. So this is something that you have to watch out for when you actually start debugging GPU code step by step. That sometimes these variables disappear, and that's okay. Okay, it's just life. That's how it works. Okay. There is an option, but again, if you do that, you're running a different code. The execution will be significantly different. You're yeah. Right. No. Yes, you can. But so that what I'm saying is, by default, it will get optimized away. If you make it on purpose, less optimized, then you can understand what's going on in your code. However, that code will be different from the one that you will be running in production mode, right? So and it comes back to parallel programming, right? So because you are typically using shared resources, I mean, in this case, it's simple because you just worry about the isolated piece of data. But as soon as you start using shared resources, then it's very important how many threads are trying to get at it at the same time and how you access it. Right? If you just reduce your occupancy by a factor of 2, then there are half the threads that are trying to do something, or maybe the blocks are now running sequentially as opposed to in parallel, and just depending on what device you're running on, it can be potentially different. So you have to think about the architecture, but just to this extent. It's not too crazy. Yeah?
You copy the vectors from the RAM to the device memory.
Yeah.
What happens if they are bigger than the device memory?
Well, it won't work. You get back a failure. You get a CUDA failure.
But would you encounter these things in real-life examples?
Oh, sure. Yeah. If you don't have enough memory, then you don't have enough memory. You get an error.
So you would have to parallelize now on the level of the computer. I mean, not on the device, but I mean, you would have to figure out a way of.
Right. So I mean, that's a design question, how your application will deal with the data. So yes, you definitely have to chop it up, right? And if it's the memory is the limiting factor, then you chop it up by memory. If it's something else, then you do it differently. But yes, I mean, If you're lucky to have big enough host memory to keep it there, that's good. If you don't, then you can leave it on disk and fetch it when you need it. But that goes beyond GPU programming. They're just general, just common sense type of thing. But yeah, so you have to work within the limitations of the device. Okay. All right. All right. So I don't know if I want to get here right now as time is going. How long do I?